Hello there! Welcome to this introductory lesson to adversarial game-playing agents. My name is Maximilian. I'll be your mentor for this particular lesson here within Udacity's Artificial Intelligence Nanodegree program. I'm really happy to be here. This is going to be a 10-15 minute introductory session to this topic. First of all, I'm just going to quickly introduce myself, what I'm doing, what I'm here for basically, and then I'm going to go through a very short presentation basically in order to talk you through what you're going to learn within this session, why it's important to learn this stuff, how it integrates within the lessons you've seen previously, basically how the techniques relate to each other, and how basically you can search for optimal solutions within a game playing framework and how you can optimize for these solutions. So, quick introduction to myself. My name is Maximilian. As I said, I'm the mentor for this course. I have been through the AI Nanodegree myself roughly 2 years ago. I am a software engineer by trade with a consultancy company in Zurich, Switzerland. I have entered the field of artificial intelligence basically through this nanodegree, just the same way that you are doing right now. It has enabled me to work on AI-related projects within my company, and I've been able to extend my knowledge considerably since then. But I always love to come back to Udacity because there's just so much content to be produced, and you have to know that the content that you're learning within this program really is going to bring you forward in your career, right? It's just the stepping stone, but just taking the stepping stone is going to bring you so much further than you can possibly imagine today. So hope that you're going to enjoy the content that we're going to discuss today together. I'll see you right back in my presentation to introduce to you the topic of adversarial game-playing agents. All right, welcome back to this presentation, this intro to adversarial game-playing agents. Just to put this back into context very quickly, previously in your nanodegree you should have seen the problem of classical search. Right. In classical search, if you recall, the general problem was that you had some agent which was initially located in an initial state, right? And its objective was to reach a predefined goal state, right? And in order to do that, the agent had the possibility to move from its initial state to intermediary states, and then in between intermediary states, up until the point where the state that the agent reaches is the predefined goal state, right? And the objective was to find the shortest path between states in order to reach the goal state. You might recall that there were different techniques, right? Uninformed search, which worked well on small search spaces, and informed search techniques, which came into play mainly as soon as the search space became untractable for uninformed search, right? So these techniques basically are similar to the ones that we're going to use here in adversarial game-playing problems, right? So what are adversarial game-playing problems, also called multi-agent game-playing problems? So the main difference, as you might extract from the name, is that you don't have a single agent anymore within your problem setup. Generally what happens is that if you think about typical game problems that you could think of, you tend to have multiple players playing the game, right? And generally players have conflicting interests in the game. Every player wants to win, right? And these objectives tend to be mutually exclusive, right? Only one player can win the game, or only a team can win the game. Meaning that in order to win the game, you have to beat the opponent, right? And so basically the difference between these multi-agent problems compared to the classical search problem is that in order basically to reach your objective, you have to sort of undermine the objective of the opponent, right? You basically have to ensure that the opponent doesn't reach its own goal. And in order to reach your personal goal, you have to also think about the fact that the opponent will try to undermine your own goal as well when it basically acts on the search space. This is a very interesting problem, basically. A lot of companies have been working on this. The complexity of the problem can get very large very quickly. We're going to look at one company that has been working on this problem for a while and which has made tremendous progress in building solutions to such problems. Yeah, so the company in question, you probably have guessed it if you're interested in AI in any way, is DeepMind, right? DeepMind is a London-based research company which has been acquired by Google a couple of years back. These people have made some of the most important advances in the field of machine learning over the past decade, basically. And the way they did that is basically they tried to solve the problem of building intelligent agents that could play more and more complex games, right? And ultimately also beat the best humans at these particular games. So we can look at a couple of examples of the games that DeepMind worked on and solved ultimately, and see basically the progress that they've made over the years and basically the exponential curve that their progress took, which is really, really impressive. If you look at the first games that DeepMind solved, it's this very, very simple Pong game, right? A video game from the 1970s. And this is a game you can see where the agent has a very, very limited number of actions it can take, right, at any given state, right? It can basically only move left or right. That problem may seem kind of simple nowadays, but at the time, obviously, the field of machine learning has made tremendous progress in the past decade. And this what's considered a complex problem at the time, and the way DeepMind solved it was already very, very impressive to the research community, because basically they built a robot that was basically capable of playing in a superhuman way, right? So way better than any human could ever play this game. So they already showed tremendous results in that instance. But then basically they moved on to work on way more complex games, right? Initially basically working on chess, beating some of the best players there, moving on from there to Go, right, which is a board game that is in some way similar to chess, but basically where the search space is exponentially larger just because the number of moves that that every player can take at any turn is in the millions, basically, whereas it's only in a couple of thousands in chess. So basically a search space that has increased dramatically between chess and Go there for their search agents, right? And the results there were impressive. Go was able to beat the world champion AlphaGo was able to beat the world champion in Go, I think, without losing a single game itself. So basically it crushed the human. And that was already very, very scary for a lot of people who were skeptical, basically, of the progress made in AI and how it could go out of control, basically, in the future. Just because, yeah, in this instance, again, this very, very narrow problem, narrow but complex problem, the machine proved to be way superior to humans. And the latest challenge that DeepMind tackled was the video game StarCraft, right? Which again adds a huge increase in complexity, simply because now suddenly the search space that the algorithm has to go through is basically infinitely large, right? There are no predefined number of moves that the agent can take. Oh, well, they are predefined moves, but there are an infinite number of them. So again, a huge increase in complexity for the search agent, and the added complexity that the agent now has incomplete information over the state of the game, right? Because again, I'm not a StarCraft expert, but I believe that initially, at least during the game, you cannot see the actions of the opponent, so you don't really know what's happening with him, but you still have to play in an optimal kind of way in this incompletely informed environment, right? And again, that's a very, very recent result. A couple of weeks ago, AlphaGo published their results there, and they showed that basically they have beaten some of the world's best StarCraft players, so professional StarCraft players. And again, I think they crushed them, right? I don't think Alpha Star, which is the name of the agent here for this particular game, lost a single game. I'm not sure about that, but at least it performed very, very well against human opponents. So again, very, very impressive results in that instance. All right, so after this short motivational section about multi-agent game playing, let's look at the main search strategies we're going to analyze in order to solve this problem. So basically, the main algorithm we're going to look at is the so-called minimax algorithm. If you recall back to classical search, one of the algorithms we looked a lot into is the depth-first search algorithm, right? Which basically tried to solve the search problem by going down the tree of states within the search space, trying to find basically the goal state within the search space, right? And ultimately spitting out the shortest path in the search space. Minimax does something similar to DFS in the sense that it will initiate at the starting state and then go down the space of states that span out from there, trying to reach the goal state. But obviously Minimax has to take into account this constraint from multi-game playing, which is that you are not the only agent playing the game, right? You have an opponent, and you and your opponent are taking turns in basically making the game evolve over time, and therefore in choosing the next states that the game is taking. And basically the assumption that Minimax makes in order to find the optimal path is your opponent is always making the most optimal moves for himself, right? He doesn't make any mistakes ultimately. And the way that Minimax models this is basically Minimax sets up a utility function, or you define a utility function that Minimax has to use in order to determine which state is the most useful for yourself, right? Basically, states which result in you winning the game have a high utility function, and states which result in you losing the game have a low utility function, right? And basically what Minimax says is that at every stage, at every turn that you have in the game, you are always going to try to maximize the utility function, whereas your opponent is always going to try to minimize the utility function, right? And basically that's how Minimax discriminates between various paths and chooses the most optimal one for yourself. Now, one of the problems with Minimax, right, similar to what happens with uninformed search strategies in classical search, is that it can very quickly happen, basically, that the depth of the tree just increases exponentially in size, right? And the problems then very, very quickly become untractable for the raw form of Minimax. And in order to handle that problem, we're going to look at two different strategies that we can use in order to make Minimax more efficient for such problems, right? The first technique we're going to look at is called alpha-beta pruning. Alpha-beta pruning is basically a strategy which is used within Minimax and which basically helps Minimax select particular branches within the search trees that Minimax can already exclude as being relevant solution branches for its problem, right? Basically, the idea is that when Minimax goes down the search tree and finds a particular solution with a certain utility value to it, if Minimax then searches for another branch of the tree and basically ends up at a node where it realizes that basically solutions through this particular node would only result in solutions with worse utility function than the one it has previously seen, it can already exclude it, right? And basically alpha-beta, in the name alpha-beta pruning, relates to these particular threshold values that Minimax will basically maintain during its process in order to basically recall whether a node with a particular utility value has to be considered or not, right? In general, using alpha-beta pruning will enable the search algorithm to basically cut the number of possible branches that it can take in half, right? So basically the exponent of the time complexity of the algorithm can be cut in half using alpha-beta pruning, so that's quite significant. We're going to look at the details and later on when we actually look at the algorithm, but this is a very, very important technique in order to make Minimax actually somewhat efficient, because the raw form of Minimax is actually very inefficient, but alpha-beta pruning helps it become usually viable for a lot of useful problems.